So previously we showed that the Riemannian Hessian operator can be related to the classical Hessian if you use essentially the exponential map, the Riemannian exponential map. Okay, so the natural question to ask then is whether that holds if instead of the exponential you use a retraction instead. Okay, so let me state the following proposition. So let R be a retraction, and suppose that in addition to that property, the usual properties of the retraction, which amongst other things include this rigidity condition, and you also suppose that in addition we have essentially a zero acceleration condition. So if you take this second derivative of the retraction evaluated at t equals to 0, right, that's equal to 0 for all tangent vectors, where d squared dt squared denotes the acceleration, right, which we defined before. Then the following is true. Then the property which had held involving the relationship between the Riemannian Hessian operator and the classical Hessian operator involving exponentials also holds true for this retraction. Okay, so that this is equal to the Hessian of the classical, or the classical Hessian of this function at the point 0x. So the proof is essentially the same as the previous proposition. So follows sort of the proof strategy of the previous proposition. Where you replace the exponential of x by this Rx throughout. Then the first remark is that the first order rigidity condition which is a defining property of a retraction implies that the time derivative of R x applied to t cos c evaluated t equals to 0, right, is equal to cos c. Okay, and then because of this, and the zero acceleration condition, so this is the zero acceleration condition. Right, we get the same result as in the proof before, right? But of course, it's like where the retraction takes the place of the exponential. Okay. So again, it's like the net effect of this is that you can use this to relate the again the Riemannian Hessian. It's like to the classical Hessian. Okay. Right. So this gives you substituting the Riemannian Hessian as the classical Hessian of f composed with this retraction defined on just Tx of m, okay, which is a Euclidean space, okay, and in particular we can use this to just look at second, or we can rewrite the Hessian in terms of second derivatives of curves. And the reason, if you recall, is that one of the properties which we had, it's like with the regular Hessian, right, is that the Hessian of f of x y paired with y, right, is nothing more than the second derivative of f x plus ty evaluated at t equals to 0, right? All right, so what that means is that if you think of this Hessian and you apply it to two vectors which are the same, right, it just involves the second derivative of of a curve, or sort of, if you will. Okay, and then the final piece of the puzzle, of course, is that through the polarization identity, you can rewrite it's like the pairing, if you will, for any pair of vectors. It's like in terms of just situations where the vectors are the same. Okay, so this observation together with the polarization sort of identity sort of gives you what you need. So let me just briefly remind you again of the polarization identity, but I won't prove it again. Right? So recall that by the polarization identity, right, that Hessian of f of x, okay, paired with c eta, right, is equal to 1/2 d squared dt squared f of Rx t of sum of these two vectors. So minus f of Rx of this minus f of Rx of the second vector. Again, evaluated at t equals to 0. Okay. All right. And that's because, okay, so if you're wondering why you get that, that's because by the polarization identity, this is equal to 1/2 Hess of f of x this minus Hess f of x, just involving the first vector, right? Okay. All right. So going from here to here is the polarization identity. Going from here to here just involves this observation that the classical Hessian, it's like satisfies this property. It's like in terms of evaluating, it's like the function f along some ray. Okay, all right. Yes. So yeah, so you have to have some zero initial acceleration condition, right? So, but this holds only for retractions with this initial zero acceleration condition. Okay, which we refer to as second order retractions. And as you might expect, not every retraction satisfies this property. Okay. So not every retraction satisfies this. So you might ask, well, what happens if you know, we throw caution to the wind and instead of computing the Riemannian Hessian operator, we instead compute this thing, even for retractions which don't satisfy this initial zero acceleration condition, right? So in particular, you might ask, if you did that, would it affect the convergence of our numerical algorithms? Okay, so not every retraction satisfies this, but it will not affect the convergence of our Newton method if you did so. And that sort of involves the following proposition. So you might ask, it's like, why is it that, you know, you don't actually need the second order condition, right, and still have convergence of your Newton method? So let me just state why that's the case. So, and more or less has to do with what happens at a critical point, okay, of the real value function. So as you might know, it's like when you do error analysis of the Newton method, all that really matters is what happens in the vicinity of the critical point. So, all right, so the proposition as follows, right? So let R be a retraction. And let V be a critical point. Of a real value function f. Okay, so what I mean by critical point obviously is that the grad of f at v is equal to 0. All right, then the following is true, that the Hessian of f at v is equal to the Hessian of f composed with rv at 0v, and this is true even if the retraction is not a second order retraction. Okay, so that's the important part, that you have the equality, it's like, of these two things at the critical points, and so that's really what matters at the end of the day from the point of view of the convergence properties. Okay, all right, so let me try to show this result. Okay, so let's do this proof. Okay, so we show that hash fv Right, so this is sort of the result we had shown earlier, right? But where we needed sort of this property that the retraction was a second order retraction, which means that its initial acceleration is 0, okay? But now we're just going to show it, it's like for a specific tangent space, right? Which is the tangent space to the manifold at the point V, where V is a critical point. So that's going to make all the difference, okay? And so this for all vector fields. So okay, so one of the things that's like we showed earlier was the following. Okay, so we showed that you can write the Hessian in terms of these directional derivatives and the covariant derivative. Okay, so all right, so now I'm going to just evaluate them at the point which is the critical point. Okay, all right, and okay. All right. So, so the second term is an element of TVM, right, applied to F. And then, since this is, of course, a critical point, of F, so this vanishes. And then all you're left with is that the Hessian of this, right, at the critical point is just this term here. Okay, so if I fix a basis, let's say E1 to En for TVM, and consider the coordinate chart. Which is defined by the retraction, right? So the inverse of the coordinate chart y1 to yn, right, is related to the retraction. Okay, so if you recall, the retraction is a map from the tangent space to a neighborhood that's like of the point, right? And the coordinate chart is sort of the inverse, right? So you're saying that these things are related via the natural inverses once you've, you know, coordinatized, if you will, the tangent space at V to M through the choice of a basis. Okay. Right. If you need to see what's going on, right? So you have let's say TXM to M related by the retraction, right? You have this mapped to Rn by mapping sort of yi maps to y1 to yn, right? And then this is the coordinate map which we have, right? So that's how the diagram commutes as related to each other. Okay. All right. And then what you have is the following. So since V is a critical point, right, of f, then the derivative of f composed with the inverse of the coordinate chart vanishes at 0. Okay, and the reason why 0 is the relevant thing is because the retraction then maps the point x, or relates the point x on M, it's like to the 0 vector in Rn. Okay, that's how that coordinate system looks like. Okay, so all right, so this implies that when we evaluate this, expression, this is equal to the sum over I of C superscript I partial derivative of the I coordinate of sum over J of this, right? And this is equal to nothing more than the sum over I and J of Ci eta J of di dj of f composed with this. But we know by the rigidity condition that d of Rx at 0 V is the identity. Okay. So these just the components. In the basis. Okay, and so this later expression is just the Hessian of f composed with the retraction, right, at 0 y. All right. So when I want to interpret this, it's like in this way, right, that rigidity condition, it's like then tells me that you know, the representation of the matrix doesn't change, if you will. Okay, so again, it's like the bottom line is that because of the fact that we have, you know, we have the relationship between the Riemannian Hessian and the classical Hessian, right, where you look at the Hessian of f composed with the retraction, this equality still holds at a critical point, right? Then again, it's like if you were to replace this Riemannian Hessian, right? If you replace the Riemannian Hessian with the expression in terms of the classical Hessian of f composed with RV, and you use it, it's like in your Newton method, it is still going to converge at the rate you expect it to, even though you don't have that equality, which you do, it's like for second order retractions, but which doesn't hold in general for more general retractions. All right, so so that's sort of all the machinery we need to then sort of formally talk about the Newton method. It's like on Riemannian manifolds, so we'll discuss that next, and we'll talk about again the convergence properties of these methods. All right, so I'll stop here for now.